In section 4.6, we're talking about graphs of composite trigonometric functions. So for the warm-up, graph each function for negative 2 pi is less than or equal to x is less than or equal to 2 pi. Adjusting the vertical window is needed. Well, what does this mean? This means that we're putting in our domain of our window as being negative 2 pi to 2 pi. So we're basically showing a domain of a total of 4 pi. Now what we're going to do after we get our window set is we're going to put in this first function, f of x equals the quantity 1.5 cosine of x all squared. Now you have to be careful how you put this into your calculator, because if you don't put parentheses in the right place, you're not going to get exactly the same function. So let's go ahead and set our window, and we need to make sure we have it set to negative 2 pi for the x minimum and positive 2 pi for the x maximum. And let's pick a scale that would be good, and I believe I picked pi over 2. So it's going to have a tick mark every pi over 2. For your vertical window, the y minimum and the y maximum, you can figure that out after you've graphed the function and see how you need to adjust that to make sure that you can see everything. But right now I'm going to put it at y minimum is negative 4, y maximum is 4, and our y scale is 1. So let's go ahead and put in our first function, which is the 1.5. So I'm going to put parentheses and put 1.5 cosine of x. Now I need to end both sets of parentheses before I do the squared. And let's see if this window shows that entire graph. And it does. So the first question you want to ask yourself is this function periodic? And it is, because we can see it start to repeat. If we look at it starting right here, we see a full cosine function, and it goes from, it looks like 0 to pi. So we can say this is a periodic function, and its period is pi. Another way you can view that is, you know that your domain right now is showing a total of 4 pi. And you can see a cosine function repeating 4 times. That's again another way to see the period of pi. So this one is periodic, and not only that, it's sinusoidal. Now how do we know if it's sinusoidal? Well, sinusoidal means that it's going to have a constant amplitude that you're seeing. You can have functions that are periodic but not sinusoidal, as we're going to see in some of these other examples, but this one is a sinusoidal function. So now let's look at our next example, which is x squared times the cosine of x. I'm going to clear that one out, put in x squared times the cosine of x, and graph that one. Now at first glance, it doesn't appear that this function is periodic, but we can't be certain of that unless we extend our domain on this, because we don't know if this exact same graph might be repeating. So let's go ahead and change our window so we can see more, and let's put in negative 4 pi. And 4 pi. And that should show more of the function. And so what we're seeing is that this figure right here in the middle isn't repeating, so this is not a periodic function. Therefore, it's definitely not a sinusoidal function either. So let's move on to number 1, where it says tell whether each function is a sinusoid, and if it is, express it as a single sinusoid. If not, explain why it is not. So going back to our smart notes, we've now looked at these two examples, and it says a sinusoid is a function that can be written in these two forms. And here's our literal equations for sine and cosine, and these are what we've seen all along for sine and cosine. You have to figure out what a is, what b is, what h is, and what k is. So looking at these next two examples, let's plug in this first one. So I've put the function into the calculator. Now let's graph it. and see if it repeats at any point. So if we look to the left of the y-axis, we see it looks like a heartbeat. And if we look to the right of the axis, we see that exact same part of the function repeated. So this one is a periodic function, but it would not be considered to be a sinusoidal function because the amplitudes of each of these local maximums and local minimums is changing each time. So we would say no, it's not sinusoidal because the amplitude is changing. Now let's look at our next example, part B, and let's clear this out. And if you need to pause this, please do so. All right, so I've put the function into the calculator, and let's graph it. And I should have changed my window back to, and I'm going to do that in just a second. I want to change it back to negative 2 pi to 2 pi. Just so it's a little bit easier to calculate what we need to on this. But we do see that we have a periodic function and the amplitude is consistent, so we do have a sinusoidal function. Now let's change our window back to negative 2 pi and 2 pi. And that's going to make it a little bit easier to see. Now for these composite trigonometric functions that are sinusoidal functions, we're going to rely on our calculator entirely in order to figure out what the function is going to be. Now remember, we could write this as a sine or as a cosine function. Now the period that I'm going to focus on is I'm going to focus on this cosine function starting right here, that's upside down, going to right here. So there's 3 points that I'm really going to focus on. I'm going to focus on this minimum point here, and this maximum point here, and then this next minimum point, because by focusing on those 3 points, I'm going to be able to see the period, I'm going to be able to figure out the amplitude, and I'm going to be able to figure out the vertical rise. So let's go ahead and calculate those 3 points. So go to second, calculate, and we'll do our minimum point first. And so left bound, right bound, hit enter again. And so we get that x is 0.125 and y is negative 1.602. I'm going to write that in our smart notes for that first point. I'm going to sketch the piece of the function that we're using. So this is 0.125 and negative 1.602. Now let's calculate that maximum point. So 4. Left bound, right bound, enter. So that maximum point is at 0.910 and positive 1.602. Now I know that this next minimum point that I'm going to check is going to be at negative 1.602 because the amplitude, the minimum points are all the same. Now, but let's find the x value of that. So we're going to calculate again the minimum point. So left bound, right bound, and enter. So the x value is 1.696. Now, how do we use this? We have our key points. Well, we know that the period is going from this x value, 0.125, to this x value, 1.696. So to figure out the difference of those, we're going to do 1.696 minus 0.125. And this is going to give us our period. So in my calculator, we get that the period is 1.571. Now at this point, you might recognize that if you do pi divided by 2, you're going to get 1.571. Now it doesn't matter. You can acknowledge that that is equal to pi over 2, or you can use 1.571. But what we do know about cosine functions is that the period is 2 pi over b. So in this case, 2 pi over b equals pi over 2, or 1.571. So at this point, when we calculate this, we get b times pi equals 4 pi, so b is equal to 4. So we know one of our key values now. Now, the other thing to look at is what's happening with our amplitude, with our maximum and our minimums. Well, our minimum goes to negative 1.602 and our maximum goes to positive 1.602, so our midline is y equals 0. So that means that k is 0 because this hasn't shifted vertically up or down. So we know b, we know k, and we know our amplitude. Now we have to think we're doing an upside down cosine function, so in this case our amplitude is going to be negative. So we're going to say that our amplitude, or a, is going to be negative. Our amplitude is negative 1.602. Now the only thing we have left to figure out is what's happening with our horizontal shift. And this right here tells us where this function is starting in relationship to the x-axis. And it's shifted to the right 0.125. So h is equal to negative 0.125. So when we put this all together in a cosine function, we get negative 1.602 cosine of 4 times x minus, h is positive 0.125. And that's it. So you can see that we're heavy on our calculators in this section. And I wrote that on the wrong one. This was actually all letter B. A was not a sinusoidal function. So the next thing we talked about in class is find 3 ways to express this sine function using our literal equation g of x equals a times sine of the argument b times a quantity x minus h. So the first thing we need to do is get this into that form, and that's going to be our first equation. And so we need to pull that b out of those parentheses. So we get 3 times sine of 2. When we pull that out, we get x minus pi over 2. And this allows us to see exactly what b is and exactly what h is. So what we know is that b is equal to 2. And because our period is 2 pi divided by b, our period is actually pi for this. So this sine function is going to be repeating every pi. So now let's look at the other 2 ways that we can write this function. Remember, the only thing that changes, we could write an infinite number of functions for this, but we know that it's repeating every pi. So the only thing that's going to change is our horizontal shifting. So if it's shifting pi each time, if we wanted it to shift to the right pi, then we would need to shift it to the right another pi from pi over 2, which would be 3 pi over 2. And that's going to give us the exact same sine function. But let's say from this original red function that we wanted to shift it to the left 1 period. Well, in that case, if we started this one at pi over 2 and we shifted it to the left a full pi, it's going to be 3 times sine of 2x plus pi over 2. And when you look at these h's here, the purple, the green, and the red, they're all pi apart, so they're all 1 period apart. Okay, the next thing, find a periodic function f of x for which the period of y equals the absolute value of f of x is not the same as the period of y equals f of x. Well, a good one to try this on, first of all, we have sine of x, and let's put in our calculator under y sub 2 the absolute value of sine of x. Now we have 6 different trigonometric functions that we could try this on, but let's go ahead and start with a simple one. So let's put in just plain sine of x for y sub 1, and let's put in the absolute value. So go to math, scroll over to number, and let's do the absolute value of sine of x. And let's compare these. So the blue is showing our sine of x, like we know so well, and the red is showing the absolute value. Did our period change? Yes, it did. For the red, we see it occurring every pi. 4 of these red periods have occurred in our 4 pi window. So this absolute value is a period change. Here the period is pi, and for our regular sine of x, the period is 2 pi. Now you can experiment with the other 5 trigonometric functions and see which ones have a period change when you take the absolute value of the function and which ones do not, because they don't all have that. The last thing is the graph of each of the following functions oscillates between 2 parallel lines. Find the equations of the 2 lines and the graph of the lines and the function in the same viewing window. Well, first of all, let's look at this function in our calculator. So let's go clear out what we just did. Let's put in 1/2 x plus sine of x. And see what that looks like. Now this is a kind of weird one because it is a sinusoidal function, but this one happens to be going up by a diagonal, so it's very weird. Now let's look at what this line right here might be, and let's look at what the lower bound of this sinusoidal function might be. First of all, for this, if we only focus on the sine, our amplitude would be 1. And that's going to be significant for finding the equations of these 2 lines. And if we look at the slope of what we're adding to that sine function, the slope is equal to 1/2. So the 2 lines that are going to work for this is y is going to be 1/2 x plus 1, and y is going to be 1/2 x minus 1. Now you're going to get to play with this on your homework and figure out what happens if you're adding a constant to this function. How is that going to affect the equations of the lines? But this gives you a pretty good idea of at least the basis of what you're doing. Now let's look at what happens when we put those 2 linear equations in there. So 1/2 x plus 1, and then on y sub 3 let's put in 1/2 x minus 1. And let's see if we get the pretty graph we were hoping for. There's our first line, there's our second line, and it's hitting it perfectly. So it shows the upper bounds and the lower bounds. And that should give you enough to do your homework tonight. Good luck.